Before we can start learning about surface integrals, our first stop is to really understand parametrized surfaces. Okay? I cannot overemphasize how important it is that you clearly understand this. Whenever I get questions from students at the end of this chapter about surface integrals, and I'm helping them, when I try to see where has the student, what is the misunderstanding that the student has, it's always because they didn't completely understand parametrized surfaces. Okay? So I think it's a very straightforward concept, and I'm going to try to be as clear as possible. So a parametrized surface is basically a way to describe a surface in three-dimensional space, such as this sheet. Okay? I want to mathematically describe it. And the way I mathematically describe something, as you know from chapter 1, equations of lines and planes, is by writing down the equation for the vector that joins the origin to any point on the surface, right? So you remember that that was the parametric equation of a line, or the parametric equation of a plane was a vector r, which depended on some parameters, right? So this is exactly what we are going to do here. A parametrized surface is a vector r, which depends on two parameters, and I'm going to call them u and v, although this is of course an arbitrary choice, how you name the parameters. So what does this mean, a vector that depends on u and v? This means that this vector has three components, because this is the position vector. So the x component is a function of u and v, the y component is a function of u and v, and the z component is a function of u and v. Okay? And that's it. That's a parametrized surface. Okay? For example, this u plus cosine v and 3 minus v plus u. Here I wrote three random functions of u and v. Some of them don't depend only on u, but that's okay. That's still a function of u and v, where the dependence of v is nothing. So this would define a surface in three-dimensional space, because for each value of u and v, I'm getting a position vector r. Okay? So let me show you an applet to show you how this would work. So here I'm showing, on the left, I'm showing you what we call the parameter space. So imagine that this grid here represents the different values of the two parameters u and v. Okay, so imagine that in this x-axis we have u, and in the vertical axis we have v. Okay, and I have two sliders which correspond to u and v. So if I change u and v, I'm changing my position on the parameter space of u and v. Okay. Now, for each value of u and v, I can come back here, I can substitute my value of u and v, and I get a vector r. Or in other words, I substitute u and v, and I get x, I get y, and I get z. Okay? For example, here, if I substitute u equals 0 and v equals 0, I would get x equals 1, y equals 1, and z equals 3. Okay, so that's a position in space. So therefore, for each value of u and v, I get a position in space. And this is what I represent here on the right. Okay, so this is a three-dimensional surface, and I'm representing the origin of three-dimensional space. And now the red arrow here is the vector r that joins the origin to a position on the surface. And you can see that if I change the value of u, or I change the value of v, the position vector is moving throughout the surface. So you can see that this transformation r of u and v, or this parametrization of the surface, is transforming a flat space of parameters u and v, it's transforming it into a surface in three dimensions, a curved surface, okay, such that each point in this grid on the left corresponds to a point in this grid on the right, as you can see here by the red point. Yeah, and this means that in some sense you can draw the same way that we drew here a grid separating the different values of u and v. We can draw the corresponding grid in the three-dimensional space. So whenever I substitute values u and v that are exactly at a grid point, for example, now we are at the intersection of these two lines, so you can see that the corresponding vector r is also at the intersection of the two lines. If I now change v, I reduce it to the next intersection, you can see that vector r moved to the next intersection. Okay, so that's why the grid in transform space has been transformed into this. Sorry, the grid in the parameter space of u and v has been transformed into a grid in this curved surface, which is the surface we are describing. Okay, so in some sense, you could somehow forget about parameter space and just think about the real surface as having this grid in which different values of v give rise to different lines, yeah, like they are labeled here, while at the same time different values of u, parameter u, give rise to different lines in this direction, which are labeled here, which means that having these 2 degrees of freedom, u and v, I can always move as much as I need in u and as much as I need in v to reach any point I want. Okay, so imagine I want to reach this point of the surface. Well, I know that v is between 1 and 2 because those correspond to these 2 lines. So maybe v should be 1.6 to reach this point. And then u has to be between -1 and -2. So here I would say -1.6 also. Okay, so if I choose u and v equals -1.6, I would reach a vector r which points from the origin to whatever point I want on the surface. In this case, this point here. Okay, so I hope this is all clear. And these really nice and beautiful figures, they come simply from an equation like this. It's simply a vector of 3 components, and each component depends on u and v. Okay, it's the same thing. In fact, if I get this function, which I wrote completely at random, it wasn't planned, and I now write it in Mathematica, which I just did, it's this function here, and I plot the surface that this corresponds to, we get this strange curved thing. Okay, but you can see that each value of u and v results on a point along this surface. Okay, so that is it. That is a parametrized surface. It looks as simple as a function which has 3 components, x, y, z, and each of them depends on u and v. Okay, another way of writing parametrized surfaces is by using the black box method, where this is basically like a function that has 2 inputs, u and v, the 2 parameters, and it has 3 outputs, x, y, and z, which is the position vector. So in this way, our 2 sliders can be used to change our position along the surface. Let's see some actual examples instead of using random equations like this. For example, do you remember the parametric equation of a plane? You remember that this was r of 2 parameters, u and v, is equal to r0, which is some position of the plane, plus u times a vector u, plus v times a vector v. You remember this, right? Where u and v were 2 vectors contained in the plane. And this created a plane where if I draw here the origin, and I draw here the plane, so we had a vector r0, and then we needed 2 vectors u and v, such that now we could draw this grid in this infinite plane here, right? So for each value of our 2 sliders, the scalars u and v, which are the parameters, I can move through this grid, which is the infinite plane. So you remember that, okay? So that would be the parametric equation of a plane, which you could also write as x0 plus u times ux plus v times vx, y0 plus u times uy plus v times vy, and z0 plus u times uz plus v times vz. Okay, where I simply substituted the fact that r0 is x0, y0, z0, u vector is ux, uy, uz, and v vector is vx, vy, vz. So you can see that indeed the equation of a plane is simply three equations which are a function of u and v. In the case of a infinite plane that we were seeing in chapter 1, these are linear functions because we only have constants and u and v to the power 1. So that's why this forms a straight plane. If we do non-linear functions, such as having u squared or having a cosine, then we are getting bent surfaces. It's a non-linear surface, okay? Let's see an example of a very well-known bent surface. This would be a spherical surface. So you remember that we defined spherical coordinates and they looked very much like this, okay? But what if you fix the radius r? So we fix the radius little r equal capital R, and we treat that as a constant. Then we are only left with two variables, theta and phi. So these two variables, which I colored here in cyan, these are now treated as our two parameters u and v, okay? So instead of u and v, I'm now calling them theta and phi. And those are going to be our new parameters. So as we change theta and phi, x, y, and z are going to change. And since we were using spherical coordinates, we know what theta and phi represent. Phi represents the angle around the z-axis, so phi equals 0 keeps us on the x-axis. Then as we increase phi, we move around in this direction, yeah? As we increase the values of phi, we move around the z-axis. So if we are at a fixed point, this is like the surface of the Earth. You can use the longitude to determine in which direction you are, east or west, yeah? So this phi would be like our longitude. So if you want to move east, you increase the longitude. And now we also have theta. And theta is the angle with respect to the z-axis. So this angle here, yeah? So this means that if you are at the North Pole, theta equals 0. And if you move towards the equator, theta is moving towards pi over 2. Okay? So by moving theta and phi, you can specify a latitude and a longitude, so you can be anywhere on the surface of this sphere. Okay? So this would be the parametrization of the surface of a sphere with a constant radius. Another example would be this curved lateral surface of a cylinder, and then you could use cylindrical coordinates. So you remember cylindrical coordinates were given by rho cosine phi, rho sine phi, and z. So if we now fix rho to be constant, for example, we say rho equals r, constant. So then we arrive at this equation of x, y, z, which now depend on phi and z only. These are the only variables that we have. So phi and z now play the role of our parameters u and v. Okay, so for different values of phi and z, you get different positions x, y, z, which is the same as saying you get a vector r. And I won't talk you through it, but think about this yourself. How does changing z and changing phi move you throughout this surface, so that you can reach any point on the curved surface of this cylinder by choosing an appropriate value for u and v, or in this case for phi and z, which are our two parameters. Okay? So I hope this is super clear, and this is really important. Please make sure you have these concepts clear, the concept of parameterized surfaces, and the rest of the chapter should be fairly easy and smooth. Okay? So see you in the next video.